Hello guys and welcome back to my channel Interview with Bernie, and today in the 18th video of our graph playlist we will learn about the bipartite graph. So let's first understand that what is a bipartite graph and how we will identify that whether a graph is a bipartite or not. So according to the definition of the bipartite graph, a graph is said to be bipartite if we can color the entire graph by two colors such that no two adjacent vertex or node have the same color. So let's first understand that what does it actually means. So here if you look carefully, I have two graphs over here. This is graph 1 and this is graph 2. Now let's see whether these graphs are bipartite or not. So according to the definition of the bipartite graph, what we have to do, we have to color the vertex or the node of this graph by two colors. For example, let's take two colors. One is green and another as red. So for the first time, let's color the first node of our graph, that is the node 0, by red. So here if you see, I'm coloring this as red. So we are done with coloring the first node of the graph. Now according to the definition of the bipartite, the adjacent node should be of opposite color. So over here what we will do, we will color the adjacent vertex with green. Fine. Now what we'll do, again we will see what is the adjacent node of 1. So here the adjacent node of 1 is 2, and here if you see, we can color this node with the same color, that is red. And thus if you see these three nodes, these three are in opposite color. And in this way, we have to keep on coloring each and every node of the graph such that no two adjacent nodes are having the same color. And if we can do so, then only we will conclude that the graph that is given over here is a bipartite graph. So let's see whether we can color this entire graph by the two colors or not. So here if you look carefully, we have the next node as 3. And since the node that is connected with 3 is 2, which is colored as red, so what we'll do, we will reverse the color and we will color it with green. Fine. Next for the node 7, which is connected to node 2, here also since this node 2 is colored as red, so we will color this with green. And in this way, we will keep on doing so. So over here, if you see, we will color the node 4 with red and node 6 with red. Similarly, we will color the node 5 with green. I hope this is clear. And what we did, we used two colors. One is green and another is red. So here if you see, with the help of two colors, we have completely colored each and every node of the graph, and here each and every adjacent node are of different color. So we can conclude that this graph is a bipartite graph. Clear? Now with the same rule, let's see whether we can conclude that this graph is a bipartite or not. So here what we'll do, we will similarly use the same two color, that is red and green. So here for the first case, here on the node 0, we will mark it as red. Similarly, since the node 1 is connected to the node 0, we have to make an opposite color, that is here we will mark it as green. Similarly, node 2 will get colored with red. Node 5 will get colored with red. Similarly over here, since node 3 is connected to this node, so it will get opposite color. So we will color it with green. And here if you look carefully, this node 4, since it is connected to this node and this node, so ideally if I go from this direction, it should be colored with green. But here if you see, if I go from this direction, these two are getting same color, means there lies a problem over here, means we are not able to color the two adjacent node with different color, and hence we can conclude that this graph that is given is not a bipartite graph. So this is actually the main definition of the bipartite graph. I hope this is clear. What is the actual definition of the bipartite graph? This is quite simple and easy to understand. Now keeping this definition in mind, let's see a few more examples so that we can derive some observation out of it which will help us to solve our problem. So if you look carefully, let's take few more examples over here. So here you can see I have taken one more example over here. Now let's color it according to the rule of the bipartite graph. So what we'll do, we will first color this with green, then it will go with red, then the node 2 will get colored with green, this will color with red, this will again get colored with green, this will again get colored with green. Now here if you look carefully, there is a key observation, that is any graph that is linear in nature, means there is no cycle that is present in the graph, that graph have to be a bipartite graph. Because very obvious, since there is no loop over there, so there is no chance that two nodes will be having the same color. So we can clearly understand that all linear graph means which doesn't have a cycle in it have to be a bipartite graph. This is our first observation. So whenever in the interview you get a graph that is a linear in nature, you can blindly tell that that graph is a bipartite graph. Now let's see how this observation will differ if a graph have a cycle in them. So here if you look carefully, these two graphs that we have taken over here, both have a cycle in it. This is one of the cycle and here also we have a cycle in it. And how to find a cycle in a graph, I have already told you in my previous video. I think I have created 4 or 5 videos of how to detect a cycle in the graph with the help of the BFS and the DFS approaches. But let's now see how this cycle in the graph will differ our answer for the bipartite graph. So here if you look carefully, if I take few more examples of the cycle, you will see a peculiar behavior. And that is, for example, here I have a graph something like this, which is a cycle. Now, if I just start coloring this graph, for example, I color the first node with green, the next node with red, again the next node with green, and again the next node with red. Fine. So this is basically a bipartite graph. Now, if I take one more example, so for example, this is another graph, and if I start coloring over here also, so let's take this is red, this is green. Similarly, this will become our red, this will become green, this will become red. And here if you look carefully, here the two adjacent vertex are getting the same color, which violates our definition of the bipartite graph. And thus we can conclude that this graph is not a bipartite graph. And if you look carefully, there is a key observation over here. That is, if a cycle has an even number of nodes, then that graph is a bipartite graph. And if a graph have a cycle with an odd number of nodes, then that graph is not a bipartite graph. You can take few more examples to prove this fact. So let's take another small example. So here if you see, I have a graph which is having a cycle but of odd length, and here if you see, this is not a bipartite graph, because here if you see, if I color the node 1 with red, node 2 with green, then there is no option for node 3 to be colored with the opposite color. Thus, a graph having a cycle with the odd number of vertex cannot be a bipartite graph. Hopefully, this logic is clear. So these are the two main observations that you have to keep in mind for proving that a graph is a bipartite or not. Now let's see how we can prove that the graph is a bipartite graph or not with the help of the algorithm. And the algorithm that we will be using today is with the help of the BFS approach. I told you repeatedly, BFS and the DFS traversal are the key concept that you need to know to solve most of the problems on the graph. And similarly over here also, we will use the BFS concept or the BFS traversal to prove that a graph is a bipartite or not. So let's see how we will do it. So here if you see, I have taken the same example that we were discussing over here. So this is the example that I have taken. And let's see with the help of the BFS approach, how we can prove that a graph is a bipartite or not. So as you know, to run a BFS traversal on a particular graph, we need an additional data structure, and that is a queue. So similarly over here also, to implement the BFS traversal, we will define an auxiliary data structure called as queue. So here we are having an auxiliary data structure called as queue. Now since the concept of the bipartite graph tells that we have to color the graph, so obviously we have to keep track of which node we are coloring with what color. And to keep the track of that also, we have to use an additional data structure as an array or a hash map. So over here we will be using an array to understand the logic. Now why I have told you that we can also use a hash map? That is, always remember, if a graph start with the zero-based indexing, then use an array. Otherwise, use a hash map to keep track of it. Because if you have gone through my previous video, I have already told you that if the graph start with a one-based indexing, it will definitely give you a lot of problem if you are using an array as your auxiliary data structure. But here, since our graph starts with 0, we will use an array over here to understand the algorithm. So what we'll do, we will declare an array called as colors, which will keep track of all the colors of the nodes by which we are coloring. And here, for the first time before we start coloring the graph, we will predefine each and every index with -1. -1 indicates that the graph is uncolored. So what we'll do, we will put -1 of this color array. I think this is clear. Now what we'll do, according to the definition of BFS, we will start our iteration with a starting point, and let's here take 0 as our starting point. So we will start our BFS traversal from the node 0. And what we do in the BFS traversal, we first put the node in our queue data structure. So here we will put the first node of our graph, that is 0, in our queue. That is our starting point. And since here 0 is our starting vertex, we will also color the node 0 with any of the color, either green, red, or any of the color as you want. So here what we'll do, to color a particular node with red, we will identify red as 0, and if we are coloring it with green, we will mark it as 1. Now since we are starting with the first index, that is the 0th index, we will color it with red, and since we are coloring it with red, means here we will put it as 0. Clear? Now we can start our BFS traversal. So what we'll do, we will first pop out the element from the queue. So here the first node got pop out, and here if you see, the first node is 0. So this goes out from here, and we will check what are the neighboring nodes of the node 0. And here if you see, the neighboring node of the node 0 is node 1. So we will check the node 1. And here if you see, node 1 is uncolored because the value over here is -1. So this node is still not colored, and we have to put some color into it. And what color we will be putting? We will be putting the opposite color that we have used in the node 0. So the opposite color of node 0, that is here we have used red. So here we have to put green. And thus what we'll do, we will mark this vertex as 1. Hopefully this is clear. And what we'll do, we will push it in the queue. So right now, two of our indexes are already colored, 0 with color red and node 1 with color green. This is fine. Now what we'll do, we will pop out this element from the queue. Here the node is 1, so queue is right now empty, and we will check what are the neighboring nodes for the node 1. And here if you see, for the neighboring node of node 1 is 0 and 2. Now we will go to the node 0 and we will check whether the node 0 is already colored or not. Here you can see the value of this index is not -1, means this is colored, and also this is oppositely colored, means here the node 1 is colored as green and the node 0 is colored as red. So it is still a valid color. So what we'll do, we will skip it. Now what we'll do, we will take the next neighboring node, that is node 2. So we will push the node 2 into our queue and we will color it. And what color we will put? We have to put the opposite color of node 1. So the node 1 is colored with green. So what we have to put for the node 2? That is red. And to put the red, what we will do? We will mark it as 0. Clear? So node 2 got colored with red. Now what we'll do? We will pop out the element node 2 from our queue. So node 2 comes out over here. And again we will check what are the neighboring nodes. So neighboring nodes of node 2 are 1, 3 and 7. Here if you look carefully, node 1 is already marked as green, which is opposite of node 2 because node 2 is red. But here node 1 is green, so it is an opposite color. So this is a valid combination. Now what we'll do, we'll go to the next node, that is node 3. We will check whether node 3 is colored or not. Node 3 over here is not colored because it is set to -1. So what we have to do, we have to put the opposite color over here, and the opposite color of node 2 is nothing but green. So here what we'll put, we will put 1 over here since we want an opposite color, and we will push the node into the queue. So we are done with the node 3. Similarly, we will take next neighboring node, that is node 7. Here we will check whether the node 7 is colored or not. Here if you see, it is -1, so it is still not colored, and we have to color it. And which color we have to use? We have to use the opposite color of the node 2, and that is green. So here also we will mark it as 1 and we will push it in the queue. I hope it is clear that how we are using the BFS approach to color each and every nodes in our graph. Now what we'll do, again we will start our traversal and we will pop out the element from the queue. So here the node is node 3. So let me color this node 3 and 7 with green over here. We will check the neighboring nodes of node 3, and here if you see the neighboring nodes are 2 and 4, and here if you see node 2 is already colored and it is in opposite color because the color of node 3 is green and the color of the node 2 is red. So this is a valid combination. So we will skip it. Here if you see next neighboring node is node 4, and you can see node 4 is marked as -1, means uncolored. So we have to place the opposite color over here, and the color of node 3 is green, so we have to put red over here. So what we'll do, we will put 0 in this cell and we will put node 4 in our queue, and thus our node 4 gets colored with red. Fine. Now in the next step, we will pop out the next element from the queue, which is node 7. So node 7 comes out and we will check what are the neighboring nodes of the node 7. It is 2 and 6, and here if you see node 2 is already colored, that is an opposite color of node 7, that is here it is green and here it is red, so it is valid combination. Now we'll go to the next node, that is node 6. Node 6 is marked as -1, means uncolored, so we have to put the opposite color, and opposite color of node 7 is red, so we will mark node 6 with red color. So here red color means 0, and here we will put node 6 in the queue, and also we will mark it as red. I hope this is clear. Now we are at the last node, and that is the node 5. And how we will go to the node 5? We will first pop out the element from the queue, that is the node 4, that is the next element over here, and we will check what are the neighboring nodes of the node 4. And the neighboring nodes are 3 and 5. And here if you see 3 is already marked as green, which is opposite of node 4, so it is fine. Now the next neighboring node that is present is node 5, and here if you see node 5 is marked as -1, means uncolored, and here we have to place the opposite color of node 4, and that is green. So here we will mark this node as 1, and thus our node 5 get colored as green, and we will push it in our queue. So we are done with node 4 also. So here we are done with all this node. Now comes the next node, that is the node 6. So we pop out the node 6 from the queue. We are checking what are the neighboring nodes of the node 6, which is 5 and 7. And here you can see node 5 is already marked as green, which is an opposite color of node 6 because node 6 are red over here. So it is fine. Again, we are checking what are the other neighboring nodes, which is nothing but node 7. And here the node 7 is marked as green, which is again an opposite color of node 6. So here we do not have to color anything because both the nodes are already colored. So we are done. So the next node in our queue is node 5. So we will pop out the node 5 over here, and we will check what are the neighboring nodes of node 5, which is 4 and 6. And here if you see both the nodes 4 and 6 are already marked as colored, and it is an opposite color, that is red. So it is fine. We do not have to do anything. And that's it. We are done with the complete traversal, because here at the end our queue is completely empty, just the way we do the BFS traversal. And once the queue is empty, we stop our BFS traversal over there. And if you see right now, our graph is completely colored over here. And here if you look carefully, each and every adjacent node are in opposite color, and thus we can easily conclude that this graph is nothing but a bipartite graph. I hope this is clear how we are marking colors into our nodes, and we are proving that our graph is a bipartite or not. So here we are using a simple BFS traversal or a brute force approach to color each and every nodes of the graph. So far we have seen a happy path, means this graph we already knew that this was a bipartite graph, and thus here we have run the BFS algorithm to prove the same. But here let's now take a non-bipartite graph and let's see how this algorithm will work over here, and then we will implement this complete logic that how to detect that the graph is a bipartite graph or not with the help of the code. And believe me, understanding this logic is the crucial thing, and once you understand this logic, implementing it with the code is very easy, because if you already understood, this is the simple implementation of the BFS traversal that we are doing. Only modification that we are doing in the BFS traversal, that is each and every index we are coloring with the opposite color. That is the only point that you have to keep in mind. Now let's take a small example of a non-bipartite graph and let's prove this algorithm. So here if you see, this is our graph right now, and this is the adjacency list of the graph. And here also we are using our data structure that is called as queue and the color array over here, and we will be coloring it with the two colors that is red and green, and red will be denoted with 0 and green will be denoted with 1. So let's get started. So the first thing that we will do, we'll first start with starting index, and let's take an example that the starting index is nothing but the node 0. So we will push the node 0 into our queue and we will mark it with red color. So here we will mark this as 0, means color red. So we are done with the initial setup. Now what we'll do, we will start our BFS traversal. And as you know, by the concept of the BFS traversal, we pop out the element from the queue. So we pop out the first element over here and we check what are the neighboring nodes of the node 0. And here if you see, the neighboring nodes of the node 0 is nothing but node 1 and node 2. So let's go to the first node, that is node 1. So here if you look carefully, we will go to the node 1 and we will check that the node 1 is already marked as -1, means it is not colored. So what we will do, we will put the opposite color of the node 0 and that is green. So we will mark it with green, that is 1 over here. So node 1 is marked with green and we will push it into our queue. Fine. Now what we will do, we will check what are the other neighboring nodes for the node 0, and here if you see, other neighboring node is nothing but node 2. So here if you see, the node 2 is also marked as -1, means uncolored. So we have to color this node and we will put the opposite color, that is we have to put it green over here. So node 2 is already marked with green. Now what we'll do, we'll again start our BFS traversal from the node 1. So we will pop out the node 1 from our queue and we will check what are the neighboring nodes. And here if you see, the neighboring nodes of the node 1 is nothing but node 0 and node 2. And here if you look carefully, the color that is allocated to node 0 is red. So this is opposite color because node 1 here is marked as green and the node 0 is of red, which is fine with this algorithm. So it is not an issue. Now when we will go to the next node, that is the node 2, here if you see, node 2 is already marked as colored because it is not -1, but it is colored with 1, which is same the way the node 1 is colored, because here both the color value is same, means both the colors are same, and thus we can tell that whenever there is an adjacent node or the adjacent neighbor present over here which is already marked as color and having the same value, means the same color, we will tell that this graph is not a bipartite graph and we will return false over here, means we will tell that this graph is not a bipartite graph. I hope this is clear that how we are detecting whether a graph is a bipartite or not. So the logic is, whenever we are coloring the nodes, we are checking that whether the neighboring node is colored or not. If it is not colored, we are placing the opposite color. But if it is colored, we are checking whether it is having the same color or not. And if it is having the same color, means there is some problem, and thus we detect that the graph is not possible to be a bipartite and we will return false from here. And this is the total algorithm of how you should define that a graph is a bipartite or not. So I hope you are clear with the concept of how to detect a bipartite graph with the help of the BFS concept. And if you are clear with this concept, implementing this algorithm is very easy. Let's now see how to implement this whole concept with the help of the Java code. So let's start with the implementation and let's see how we will implement it with the help of the Java code. So here also if you see, I'm using the same pattern of coding that we are using for the entire playlist. So here we have the graph object by which we define a particular graph data structure, and here we have the main functionality where I have defined two graphs, that is one is a bipartite graph and another is a non-bipartite graph with which we were discussing so far. So here these are the two graphs over here, and from here we are calling the function isBipartite graph using the BFS approach. So I hope this is quite simple and easy to understand if you are following my style of coding in this complete playlist. So let's now see the actual implementation of how we are detecting whether a graph is a bipartite or not with the help of the BFS approach. And here lies the meat of this complete algorithm. And this is the only 10 lines of code that you have to know to prove that a graph is a bipartite or not. And believe me, this is quite simple. So let's see what we are doing. So here, just the way we do a BFS traversal, we are defining a queue over here. And as we have discussed, we need an additional data structure that is a color array, which will keep track of which vertex got colored with which color. And for that, here we are using a colored array. Here you can also use an hash map to keep track of all the colors. But to keep it simple, here I'm just using an array over here. Now what we are doing, we are simply initializing the colors object with -1, means none of the nodes got colored till now. Now we will start our BFS traversal. And what we do for the BFS traversal, we start with the first index. And here the first index is nothing but node 0. So we are pushing the node 0 into our queue and we are marking the color of the node 0 with 0. So for example, here 0 means red. So we are coloring the first node with node 0. Now what we'll do, we'll start our BFS traversal. And how we are doing the BFS traversal? We have to simply iterate over the queue till it gets empty. And here, for the first time, the queue is having the vertex that is node 0. So we'll pop out the element from the queue, which is nothing but the node 0. And we will check what are the neighboring nodes of the node 0. And the neighboring nodes of the node 0 is nothing but node 1. So we will check whether the node 1 is assigned with the color or not. And here in the first case, it is not assigned. So we have to color it. And how we will color it? We have to color in opposite color. And how we are doing it? We are initializing the value of the neighboring node with the opposite color of the current node. So here the current node was 0. So obviously 1 minus 0 becomes 1. So here look at this technique. So here we are marking it with the opposite color, and 1 minus the existing color becomes the opposite color. So with this technique, we are marking this node over here, and thus the node 1 gets colored with green. I hope this is clear. And here we are pushing that node into the queue. And in this way, we will keep on iterating over each and every node of our graph. And whenever we see that the neighboring nodes are having the same color, means that graph is not possible to be a bipartite graph, and there itself we are returning false from here. Means this is our terminating condition, that if the neighbor have the same color as the current, then that graph is not a bipartite graph. And thus at the end of this complete iteration, if we can color all the vertex of the graph with no problem, means we have successfully colored our graph, and we can conclude that that graph is a bipartite one. And thus here at the end, we will return true from here. This is the complete logic that we have discussed for the last few minutes. So let's run this algorithm and let's see whether it is working fine or not. So here if you see, we are defined two graphs. One is a bipartite graph and another is a non-bipartite graph. So let's click on run. And great, here you can see the first graph returns true, means this is a bipartite graph, and the next one return false, means this is a non-bipartite graph, because it is having only a 3 node, and you know any graph with a cycle with an odd number of index should not be a bipartite graph. And thus we have proved that how to detect whether we can classify a graph as a bipartite or not. So hopefully you have completely understood that how we are implementing this logic to prove that whether a graph is a bipartite or not. So in our next video, we will see how to implement the same logic but with the help of the DFS traversal. So if you have liked this video and if you have found this video useful, do not forget to like, share and subscribe to my channel and hit the bell icon so that you never miss an update from my side and you are always ready for your next interview. So see you in our next video where we will prove the same concept, that to detect whether a graph is a bipartite or not with the help of the DFS approach. So see you on our next video. Thank you.